Click the bell icon to get latest videos from Ekeeda.
Hello friends, we have seen some standard results of Z transforms and we have also seen how to apply damping rule on Z transforms. Let us see few examples solved on these results. Let us take the first example to see how we apply Z transforms to functions. The question is, find the Z transform of 3n minus 4 sine of n pi by 4 plus 5a. So we have to find Z transform of this given function. Let us start the solution. We have to find Z transform of this function. Let us apply Z transform to each of these three functions. We know that we take the constant outside and apply Z transform only to the function. So let us take the constants outside for each of the three functions. Thus we can see that in the first function we have taken 3 common outside, Z transform of n, minus we have taken 4 common outside, Z transform of sine n pi by 4, and in the last part 5a, the entire part is constant, so we took 5a outside and Z transform will be for only 1. Now let us apply the rules for Zn, Z of sine n theta and Z of 1 over here. Thus here, when we apply the Z transform of Z of n, Z of sine n theta and Z of 1, we get for Z of n, Z upon Z minus 1 the whole square into 3. Here for sine n theta, that is n pi by 4, Z sine pi by 4 upon Z square minus 2Z cos pi by 4 plus 1 into 4, the whole into 4. And for the last part, 5a into Z of 1. Z of 1 is nothing but Z upon Z minus 1. So this is the final answer. We can write that this was using formulae for Z of n, Z of sine n theta and Z of 1. Let us now take the second example. The second example is, find the Z transform of sine of 3n plus 5. Now this time we have sine of addition of angles. So first we will be opening this. Let us start with the solution. Sine a plus b formula is sine a cos b plus cos a sine b. Therefore, Z of sine of a plus b we can write as thus we get Z of sine 3n cos phi plus cos 3n sine phi. We know that in the first part cos phi is constant, in the second part sine phi is constant. Therefore, by linearity property, first we apply Z to both of them and then we take the constant part outside and apply Z only to the part of the function having n in that. We have separated the Z for the two functions. Now let us take the constant outside. After taking constant outside, you apply the Z transform of sine n theta and cos n theta. After applying the constant outside, we will apply the Z transform of sine n theta and cos n theta. So we have applied the Z transform for sine 3n and Z transform for cos 3n. That is, we get cos phi into Z sine 3 whole upon Z square minus 2Z cos 3 plus 1 plus sine 5 into the Z transform for cos 3n, that is Z into Z minus cos 3 whole upon Z square minus 2Z cos 3 plus 1. we can see that we can take certain part outside as common, and thus we can write as here. What we have done is we have taken the denominator constant, and in the numerator for the first part we had z cos phi sine 3 plus z sine phi cos 3 into z square sine phi. Correct? So from all this, when we simplified, we get z into z sine phi minus sine 2 whole upon z square minus 2z cos 3 plus 1. That gives us the answer for the z transform. The next example of z transform, let us start with that. The example is, find the z transform of n into e raised to an. Now here we have to use the damping rule, so we will be making some adjustments before that. So the adjustment made over here is, we have taken n as the function of un, and we have substituted e raised to an, we have split it as e raised to minus a whole raised to minus n, where the part inside the bracket we have considered to be k. So it becomes k raised to minus n. Thus k is equal to e raised to minus a. Now we use the damping rule and we solve the z transform. Thus, using the damping rule, how we get the function as z of n e raised to an, I have rewritten as e raised to an into n. We have reversed the order. Also, e raised to an is nothing but k raised to minus n. So we have z of k raised to minus n into n, which using damping rule we can further write this to be equal to u of kz. Correct? Because it is k raised to minus n. Applying z transform, we will get into z raised to minus n. So it's kz whole raised to minus n, which is the z transform for kz. Correct? Now thus, where uz will be equal to zn, and the value of which will be, correct? So zn, the value is z upon z minus 1 the whole square. Therefore, since the z transform of n, so zn is z of upon z minus 1 the whole square. So if this is for zn, we want for kz, it will be kz upon kz minus 1 the whole square. Let us simplify this further and get our final answer. Using zn is equal to z upon z minus 1 the whole square, we wrote the answer for z of kz, that is kz upon kz minus 1 the whole square. You can compare this. Further, when we simplify, what I have done is I have taken k common outside and cancelled with the k in the numerator. In the bracket, in the denominator, I will be left with z minus 1 upon k. Z minus 1 upon k, the whole square. Further, when I see that this k is nothing but k is equal to e raised to minus a. So this is z minus 1 upon e raised to minus a. 1 upon e raised to minus a is e raised to a. So the final answer that we get will be e raised to a into z whole upon z minus e raised to a the whole square. This is the z transform for the given required function. Let us now move to the next question, the next example to find z transform. The next example is, find the z transform of n plus p c p. This c here stands for the symbol of combination. So the solution. So the z transform of n plus p c p will be equal to, by basic definition we have written, summation from p is equal to 0 to infinity of n plus p c p into z raised to minus p. This is by the basic definition of z transforms. This further will be equal to, when we apply the values for p from 0 to infinity, we will be getting this series, which is 1 plus n plus 1 c1 into z raised to minus 1 plus n plus 2 c2 into z raised to minus 2 plus n plus 3 c3 z raised to minus 3 and so on till infinity. Let us simplify this further and see what we get as the answer. So now, simplifying the value of c over 3 parts, we can get 1 plus n plus 1 c1 will be giving us n plus 1 upon 1 factorial, 1 factorial is 1, into z raised to minus 1. N plus 2 c2 is n plus 2 into n plus 1 upon 2 factorial into the remaining part z raised to minus 2 plus n plus 3 c3 will be n plus 3 into n plus 2 into n plus 1 whole upon 3 factorial into the remaining part z raised to minus 3 dot 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 so on till infinity. Further simplifying this part, we get what we have done here is we have adjusted certain value, the signs of each term. What we have done is for n plus 1 we have written as minus of n minus 1, that is minus of this entire part, and we have adjusted the same for z. So it balances out to plus. Similarly, for the second part, again we are adjusted with two minuses and again a minus for z, but square of it, so still it's getting adjusted to plus. Similarly, for the third part also, it's minus 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 and it's minus of cube, again it gets adjusted to plus. Right, now we have done this adjustment. With this, let us see what we get the final answer. And when we simplify this further, we get our final answer as, we get this because this is a series for 1 minus z raised to minus 1 whole raised to minus of n plus 1. Or rather, we can say this is a series for 1 minus z raised to minus 1 whole raised to negative n plus 1, that is 1 upon 1 minus z plus raised to minus 1 whole raised to n plus 1. So it's basically the reciprocal of 1 minus z inverse raised to n plus 1, which is given by this particular series. This is the simplest form of the required z transform which we have solved the question for. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.